This video is about making statistical inference involving proportions. Let's have the definition of what proportion is. According to Google, proportion is a part, a share, or a number considered in comparative relation to a whole. Basically, when we speak of proportions, these are numbers which are expressed in fractions or decimals. Just like 1/4, which may be expressed as 0.25, 1/2, which may be expressed as 0.5, and when we say that 8% of cancer survivors are colon cancer patients, then the proportion of cancer survivors who are colon cancer patients may be expressed as 8/100 or 0.08. Now, when we speak of tests involving proportions, we are dealing with categorical variables. Example, when we speak of survival from cancer, whether the patient survived or not. Disease occurrence, whether an individual has a disease or not. Gender, whether an individual is a male or female. Or maybe a systolic blood pressure, which may be considered as high or normal. So this shows that when we speak of proportions, we are dealing with naturally categorical variables. Or maybe numerical variables but then converted to categorical variables upon reaching a certain cutoff. Just like systolic blood pressure, which are originally in millimeters of mercury, but then categorized as high or normal. In this video, when we speak of proportions, we are dealing with categorical variables with only two possible outcomes. Now let's start with statistical inference involving a single proportion. Now note here that we are going to make use of pi as a symbol for population proportion. Notice that when we express mean coming from samples, we use x bar. But when we speak of mean of the population, we use mu. For the variance, when we speak of the sample variance, we use s squared. And for the population variance, we use sigma squared. Now similarly, in proportions, we're going to make use of p hat as a symbol for sample proportion. And for population, we're going to make use of pi. Because in statistics, we often make use of the Greek alphabet to denote a population value or what we call a parameter. Consider that in normal probability distribution, we have z is equal to x minus the mean over the square root of variance. And since this time we're going to work with a categorical variable in which that is a random variable from what we call a binomial distribution, meaning there are only two possible outcomes in each trial from n trials in which the probability of success in each trial is denoted by pi, then z is equal to x minus the mean of the binomial distribution, which is n times pi, all over the square root of its variance, which is n times pi times 1 minus pi. And if we're going to divide everything by n, that will be x over n minus pi, all over the square root of n times pi times 1 minus pi divided by n. And when n is taken inside the square root, that will be n squared, which now leaves us with x over n minus pi all over the square root of pi times 1 minus pi over n. Now x over n here is the sample proportion, which later be denoted as p hat. And pi here is the population proportion or our hypothesized proportion. In which, as you can see here, the z-test for single proportion is very similar to the z-test and the t-test for single mean. Now, as for the assumptions involving the z-test for single proportion, first is that make sure that the samples are randomly selected. This is to ensure that there is no unbiasedness in the estimate of the true proportion. And next is to ensure that the normal approximation of what we call as the binomial distribution is considerable. Make sure that n times pi and n times 1 minus pi is at least 5. Now, the thing about working with proportions is that at times, it may require large sample size so that n times pi and n times 1 minus pi is at least 5. For example, if you're working with the data in which the hypothesized proportion is 0.001, which indicates a rare disease, to satisfy n times pi, which is at least 5, substitute pi as 0.001, then you need at least 5,000 samples. And when we increase pi, let's say as 0.10, to satisfy n times pi of at least 5, substitute pi as 0.10, then we'll be needing at least 50 samples. And on the other hand, if we're working with pi, let's say as 0.40, then we'll be needing at least 13 samples. So this indicates that the lower the value of pi, or in other words, the more rare the disease is, the larger the samples will be required by the test for proportions. Just a disclaimer, this is not how sample size are calculated in research, because sample size calculation deals with the level of significance, the margin of error, the power of the test, and others. Now let's proceed to example number 1.
In 2018, the World Health Organization reported that HIV or AIDS is responsible for 1.8% of global deaths, road injuries for 2.5%, and violence for 0.8%. In comparison, the harmful use of alcohol kills more than 3 million people each year. That is about 1 in 20 deaths, and most of them belong to the male species. More than 3/4 of these deaths were among men. Suppose that in Manila, researchers randomly selected cases and found that 920 out of 1,000 deaths caused by alcohol are among men. Do this data provide sufficient evidence that in Manila, more than 75% of alcohol-related deaths were among men? Test at 5% level of significance.
Let us check first whether the assumptions in the z-test for single proportion are satisfied. First, are the samples randomly selected? Yes, the samples are randomly selected. Next, is n times pi or n times 1 minus pi at least 5? Since out of 1,000 individuals who died because of alcohol consumption, then our value of n here is 1,000. And since the claim is that more than 75% of alcohol-related deaths were among men, then our null hypothesis is that pi is equal to 0.75. And the alternative hypothesis is that pi is greater than 0.75. Now, substituting in n times pi of at least 5, where n is 1,000 and pi as 0.75, that leads us to 750, which is obviously greater than 5. And to check whether n times 1 minus pi is at least 5, substitute n as 1,000 and 1 minus pi as 1 minus 0.75. That leaves us with 250, which is obviously greater than 5. Thus, this shows that the assumptions in the z-test for single proportions are satisfied. Now for the test statistic involving the z-test for single proportion, x over n here is 920 over 1,000, pi is 0.75, and n is 1,000. So substituting those values, we're going to have z equals 12.415. As for the critical value, since this is a z-test, then we're going to make use of the table of critical values for z-tests. And since this is a one-tailed test with a positive value of z, then at alpha 0.05, we're going to have z equals 1.645. Which you may also find using R using Q norm parenthesis 0.95. And that gives a value of z equals 1.645, which sets this area as the area of rejection, having an area of course, 0.05. Now the question is, where is 12.415? Is it in the area of rejection? Yes, it is in the area of rejection. Thus, we're going to reject the null hypothesis and conclude that there is sufficient evidence that, alternative hypothesis, more than 75% of alcohol-related deaths were among men. And as for the p-value, all we have to do is to compute for the area from 12.415 to the right. And that may be computed using R using 1 minus p norm of 12.415, which gives us a value of approximately 0, which we're going to write as less than 0.001. Which indicates that the probability that the observed value, in which in this case is 92%, computed from 920 divided by 1,000, happened by chance is just less than 0.1%. Or in other words, less than 0.001, which compared to 0.05 is relatively very small. Thus, there is no reason to doubt the alternative hypothesis. Thus, our claim is in favor of the alternative hypothesis. As for the 95% confidence interval, if you recall, the 95% confidence interval for single mean is based on this expression. Now, all we have to do is to replace x bar with p hat, and this standard error will just be replaced. Instead of pi, we're going to make use of p hat 1 minus p hat over n. Thus, to find the 95% confidence interval for the population proportion pi, we're going to make use of this expression, which indicates that the value of pi will be from p hat 1.96 times the square root of p hat 1 minus p hat over n to p hat plus 1.96 square root of p hat 1 minus p hat over n, which may be expressed also in this form. And since p hat here is 920 over 1000 and the value of n is equal to 1000, substituting those values, we're going to have 0.903 to 0.937, which indicates that the probability that the true value of the parameter pi is between 90.3% to 93.7%, which exceeds 75%. Or as we know, since this values does not contain the hypothesized value under the null hypothesis, that is why the null hypothesis has been rejected. So at 95% confidence interval, 90 to 94%, rounded off to the nearest whole number, of alcohol-related deaths were among men. And further, we may write the result as there is sufficient evidence that in Manila, more than 75% of alcohol-related deaths were among men. And then we may write the p-value of the z-test in parentheses. Results show that 92%, which is our sample proportion, and this is our 95% confidence interval for the parameter pi, of alcohol-related deaths were among men. Moving on, let's have the statistical test involving two proportions. Note that this test is applicable when you are comparing two proportions from two separate groups. And similarly, n times pi here, although this time pi is estimated by p hat, must at least be 5 in both groups. And consider that n sub 1 and n sub 2 are the sample size of the two groups. And similar with the test for the independent means, wherein we're not interested in the actual values of mu sub 1 and mu sub 2, in the test for two proportions, we're not interested with the actual values of pi sub 1 and pi sub 2, but rather we're interested in the difference of pi sub 1 and pi sub 2. And consider that the first proportion, which is denoted by p hat sub 1, is the x over n of the first group, and the second proportion, which will be denoted by p hat sub 2, is the x over n of the second group. And this time we have what we call as the overall proportion, which is denoted by p hat, which is simply the sum of x divided by the sum of n. Let's take a look at the second example.
It is reported that more women are diagnosed with Alzheimer's disease than men. To test this claim, 90 women and 80 men of at least 70 years of age were selected, and results show that 23 and 9 have the disease respectively. Do this data provide sufficient evidence that the occurrence of Alzheimer's disease differ with men and women? Test at 5% level of significance.
So in this problem, we have two groups of patients, group of women and group of men. And it is said that 23 out of 90 women, while 9 out of 80 men have Alzheimer's disease. So that gives us p hat 1, which represents the proportion of women, which is 23 over 90, and p hat sub 2, which is the proportion of men, which is 9 over 80. Now, checking for the assumptions, we have to compute first what we call the p hat, which is the overall probability of success, which in this case, since there is a total of 170 patients coming from 90 and 80 women and men respectively, and a total of 32 patients having Alzheimer's disease, then the overall probability here is 32 over 170. And further, we may compute for 1 minus p hat, which is 138 over 170, which is basically 1 minus 32 over 170. Thus, checking for the assumptions, if n sub 1 represents the number of women, which in this case is 90, then n sub 1 times p hat gives us 16.94, which exceeds 5. And for the other one, that is n sub 1, so still that is 90. 1 minus p hat, which is 138 over 170, gives us 73.06, which still exceeds 5. For the other group of patients, which in this case are men, in which the total is 80, so that will be our n sub 2. So that is 80 times p hat, which is 32 over 170. That gives us 15.06, which exceeds 5. And for the other one, n sub 2, which is still 80, 1 minus p hat, which is 138 over 170, which gives us 64.94, again exceeds 5. And since all of these values exceeds 5, then that indicates that we may make use of the z-test for two proportions. And since this problem is asking if the data provides sufficient evidence that the occurrence of Alzheimer's disease differ with men and women, then our null hypothesis is that the proportions of Alzheimer's disease among men and women are equal, which indicates that the occurrence of Alzheimer's disease do not differ with men and women. And on the other hand, for the alternative hypothesis, the proportions of Alzheimer's disease among men and women are not equal, or in other words, the occurrence of Alzheimer's disease differ with men and women. And applying the z-test for two proportions, our p hat 1 again is 23 out of 90, p hat 2 is 9 over 80, and the overall p hat is 32 over 170, and 1 minus p hat as we computed was 138 over 170. And of course, n1 and n2 here are 90 and 80 respectively. And of course, under the null hypothesis, since the population proportions are assumed to be equal, then this value is assumed to be 0 under the null hypothesis. And computing for the value of z, we're going to have 2.38167. As for the critical value, still we're going to make use of the table of critical values for z-tests. And since we performed a two-tailed test here at alpha 0.05, then our critical value is positive and negative 1.96, which may be computed using Q norm of 0.025 and Q norm of 0.975, which again sets this part of the normal distribution as the area of rejection, indicating that the area on the two sides of the tails are both 0.025, so that when added together, that gives us 0.05. Now, is 2.38167 in the area of rejection? Yes, it is in the area of rejection. Thus, we're going to reject the null hypothesis and conclude that there is sufficient evidence that, then the alternative hypothesis, the proportions of Alzheimer's disease among men and women are not equal. And further, we may compute for the p-value simply by getting the area here. And since this is a two-tailed test, we're also going to get the area from z equals 2.38167 to the extreme, represented by this region. And we may compute this region using p norm of negative 2.38167 and the area here, which is 1 minus p norm of 2.38167, and add them together to get the p-value. And applying that in R, we're going to get 0.017, which indicates that the probability that the observed value or having a difference which is not 0, represented by the difference of these two fractions, happened by chance is just 1.7%. Or in other words, 0.017 compared with 0.05 is relatively small, thus there is no reason to doubt the alternative hypothesis.
Next we're going to have is the statistical test involving two or more proportions, which is called
อาจารย์นะครับเรียกว่าชี้สักแควชี้สักแควชี้สักแคว It's not chi-square, but rather it is called as the chi-square.
Ow. Chi-square. Chi-square. Chi-square.
Now, in the chi-square test of homogeneity, you are comparing two or more proportions, or in other words, proportions of two or more groups. And consider that the chi-square test statistic in the chi-square test of homogeneity is equal to the sum of the squares of O minus E all over E, in which the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. And similar with the z-test for two proportions, the assumption in the chi-square test of homogeneity is that n times pi, in which pi is estimated using p hat, and n times 1 minus pi, or n times 1 minus p hat, must at least be 5. And since the chi-square test of homogeneity is applicable for two or more groups, then n sub 1 times p hat, n sub 1 times 1 minus p hat, n sub 2 times p hat, n sub 2 times 1 minus p hat, up to n sub k times p hat and n sub k times 1 minus p hat, where k is the number of groups, must all be at least be 5. As to when do we use the chi-square test of homogeneity, remember that it is used in comparing proportions of two or more groups. Just like in this example, we'd like to determine if among these 5 groups, do the onset of leukemia differ. We may also make use of the chi-square test of homogeneity to compare race. Just like in this example wherein we have 5 different races and we'd like to compare the proportion of patients with hemochromatosis. On the next example, I'll show you how the chi-square test of homogeneity is applied to determine if the proportion of patients with low level of neutrophils, also known as neutropenia, among patients with different levels of dengue infection differ.
A researcher wanted to determine if presence of low neutrophils known as neutropenia differ according to the severity of dengue fever. A total of 90 patients were gathered and results are shown below. Do the data provide sufficient evidence that the proportion of patients with neutropenia differ according to the severity of dengue fever?
Which basically asks if neutropenia occurs more to a specific level of dengue virus infection.
Test at 5% level of significance.
So basically, you have two outcomes, presence or absence of neutropenia, and you have 4 groups of patients. So it's like having p hat sub 1 as 0 out of 10, p hat sub 2, which is 11 out of 24, p hat sub 3 as 7 over 28, and p hat sub 4 as 8 over 28. And since this is just a sample of patients, the question is, if we're going to collect the entire population, are we going to have equal proportions among all patients with neutropenia among the 4 levels of dengue infection? Or there may be at least one pair of groups in which the proportions differ. So our null hypothesis is that the proportion of patients with neutropenia are all equal across different severities of dengue fever. And the alternative hypothesis is that the proportion of patients with neutropenia differ according to the severity of dengue fever. Now for the test statistic, which is chi-square, all we have to do is to get the sum of O minus E squared over E. The O is actually the observed counts, which are the values in this table that we have. So all in all, we have 8 observed counts. And each observed count has a corresponding value of E, which is called as the expected counts, which represents n times pi, in which pi is estimated using p hat. And since we have 4 columns here, then we're going to have 4n p hat. So that's n sub 1 times p hat, n sub 2 times p hat, n sub 3 times p hat, and n sub 4 times p hat, in which the value of n are the total of each column. So that is 10, 24, 28, and 28. And similar to the test for 2 proportions, wherein p hat is x sub 1 plus x sub 2, over n sub 1 plus n sub 2 since we have two groups. Since we have four groups here, then this will be x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 divided by n sub 1 plus n sub 2 plus n sub 3 plus n sub 4, which is basically the sum of 0, 11, 7, and 8 all over the sum of n, which is basically 26 over 90, which is the sum of the first row and the overall total. So we have p hat here as 26 over 90, 26 over 90, and so on. And likewise, since we have n times p hat, we must also have n times 1 minus p hat. So we're going to have n sub 1, 1 minus p hat, n sub 2, 1 minus p hat, n sub 3, 1 minus p hat, and n sub 4 times 1 minus p hat, in which again the values of n are the sum of all the columns. And as for 1 minus p hat, since p hat is 26 over 90, then 1 minus p hat is simply 1 minus 26 over 90, which is obviously 64 over 90, which is the sum of this row divided by the overall total, in which all these values are basically the ones represented by the row total times the column total over the overall total of each cell. So beginning with 0 as the observed count, its row total is 26, its column total is 10, and the overall total is 90. And what you may have noticed is that 10 here is actually our n sub 1, and 26 over 90 is our p hat. And getting the value of e, that will be 2.8889. And for convenience, we're just going to write it just beside the observed count, which is 0. And similarly, for the observed count, which is 11, its row total is 26, its column total is 24, and the overall total is 90. And similarly, 24 here is our n sub 2, and 26 over 90 was our p hat. And getting the value of that expected count, we're going to have 6.9333. And again, we're going to write it just beside the observed count of 11. And moving on, let's have the observed count, which is 7, with row total of 26, column total of 28, and overall total of 90, in which 28 was our n sub 3, and 26 over 90 was our p hat. And getting the value of that expected count, we're going to have 8.0889, which again, we're going to write just beside 7. Moving on for the observed count, which is 8, its row total is 26, column total is 28, and overall total of 90, in which 28 was our n sub 4, and 26 divided by 90 was our p hat. And getting the value of e, we're going to have 8.0889, which again, we're going to write just beside that observed count. And as for the next row, starting with 10, its row total is 64, column total is 10, and overall total of 90, in which 10 was our n sub 1, and 64 over 90 was our 1 minus p hat. And getting the value of e, we're going to have 7.111, which we're going to write just beside 10. As for 13, we're going to have a row total of 64, column total of 24, and overall total of 90, in which again 24 was our n sub 2, and 64 over 90 is our 1 minus p hat. And getting the value of e, we're going to have 17.0667, which we're going to write just beside 13. And continuing with 21 and 20, we're going to have 19.9111 as their expected counts. In other words, the observed count is the actual value or the actual count, which represents x, minus e, which represents n times pi, in which pi is estimated by p hat, which as you notice is very similar when I introduced the statistical inference involving the single proportion. Now, before you proceed with the actual calculation of chi-square, it is better to check the expected counts. And what you must notice is that the sum of the expected counts of a particular row, meaning if we're going to add these four values, the sum of those four values is actually the same sum of the observed counts. And similarly, if we're going to add all the expected counts of another row, you're going to have the same row total. So if we're going to add 7.1, 17.0667, 19.911 here, we're going to have 64. And not only that, if we're going to add the expected counts across each column, meaning if we're going to add these two values, we're still going to have 10. And similarly, if we're going to add 6.933 and 17.0667, we're going to have 24. And similarly for these two columns here. And lastly, we may inspect the proportions. Meaning if we're going to divide 2.8889 by 10, 6.9333 divided by 24, 8.0889 divided by 28, and 8.0889 divided by 28, these proportions are actually all equal to 0.28889. It is because these expected counts are computed under the assumption that the null hypothesis in which the proportions are all equal are assumed to be true. Again, the expected counts are computed under the assumption that the null hypothesis is true. That is why, again, when you divide this by this one by this one by this one, and this one by this one, they are all equal. Since the assumption in the chi-square test is that the null hypothesis is true. In other words, all the proportions are equal. Now, for the assumption of the chi-square test of homogeneity, expected counts, which are represented by n times pi or n times 1 minus pi, must at least be 5 in at least 20% of the number of cells. 1 out of 8 is just 12.5%, which does not exceed 20%. Thus, it is allowed that we make use of the chi-square test of homogeneity. Or in other words, since we have 8 cells, 20% of that is 1.6, then we're allowed up to 1.6 cells having expected count of less than 5. In other words, if in case there are 2 cells already having expected count less than 5, then that exceeds 1.6, and thus we're not allowed to make use of the chi-square test of homogeneity. Now suppose, let's say we have a 3 by 3 table, and 2 of those cells have expected count less than 5. Is chi-square test of homogeneity be allowed? Let's check. 9 times its 20% is 1.8, which implies that we're only allowed up to 1.8 cells having expected count less than 5. Since there are 2 cells which exceeds 1.8, then given this scenario, we're not allowed anymore to make use of the chi-square test of homogeneity. Now, how about there is a 4 by 3 table? Then let's say there are 2 cells having expected count less than 5. Is chi-square test of homogeneity be allowed? So that's 12 times 20%, that is 2.4. We're allowed up to 2.4 cells to have expected count less than 5. Since 2 does not exceed 2.4, then given this scenario, we are allowed to make use of the chi-square test of homogeneity. Now, if in case there are now 3 cells with expected count less than 5 and 3 exceeds 2.4, then we are not allowed this time to make use of the chi-square test of homogeneity. So to answer the question, can chi-square test of homogeneity be applied? The answer is yes. Since again, 1, which is 12.5%, does not exceed 20%, then we're allowed to make use of the chi-square test of homogeneity. Now, how do we compute for the test statistic chi-square? Remember that all of these 8 values are the observed counts. And these values in parentheses are the expected counts. So meaning, for this pair, we have observed value which is 0 and expected count which is 2.8889. Then square that over the expected count, so 2.8889. Then we're going to add that, since this is sum, with another pair which is 11 and 6.9333. So that's 11 as O, 6.9333 as the value of the expected count, then square, then 6.9333. Plus this pair, we're going to have 7 minus 8.0889 square divided by 8.0889. And same procedure follows on the other cells until we got this one, which leads to a value of 7.6244. Now, as for the degrees of freedom, we have the number of rows minus 1 multiplied to the number of columns minus 1. And since we have 2 rows here and 4 columns here, then we're going to have a degrees of freedom which is 2 minus 1 times 4 minus 1, which is 3. As for the critical value, we have a separate table for the critical values of chi-square, which basically contains the degrees of freedom, in which in this case we're going to make use of 3, and at alpha 0.05, then our critical value is 7.8147. In which chi-square is very similar to the F distribution, meaning this leftmost value is 0. It is because chi-square cannot be a negative value as well. So if this is 0.05, then this value of chi-square is Q, then CHISQ, 0.95, and then the degrees of freedom, which is 3. Since the area here is 0.95, given that this is 0.05. And still, we're going to have 7.8147, which again sets this area as the area of rejection, indicating that the area from this value up to this value is 0.05, which is our level of significance. Now, the question is 7.6244 in the area of rejection? Almost, but it's not. Thus, we're not going to reject the null hypothesis and conclude that there is no sufficient evidence that the proportion of patients with neutropenia differ according to severity of dengue fever. As for the p-value, we may compute for the area from 7.6244 to the extreme. So we may make use of p chi-square of 7.6244, then the degrees of freedom, which is 3. But this value, remember, is the area from this value to this side. Since we're interested to this side, then we're going to subtract it from 1. And that value is 0.054. And again, 0.054 indicates that the probability that the observed value, meaning that there are differences in the proportions, happened by chance by 5.4%. Or in other words, 5.4% is relatively large compared with 5%. Thus, we have a reason to doubt the alternative hypothesis. That is why our conclusion is in favor of the null hypothesis.
Now let's perform example numbers 1, 2, and 3 in R. Note that the datasets here may be downloaded using the link in the description box below.
For the example number 1, you may open the file tagay.rdata, in which our null hypothesis here is that 75% of alcohol-related deaths were among men, and alternative hypothesis is that more than 75% of alcohol-related deaths were among men. And suppose we gathered 1,000 individuals who died caused by alcohol and found that 920 of them were men. Now, as you open the file, you may type str to see the structure of the file, and further, you may take a quick look of the file by typing tagay. And as you will see, there's only one essential column here, which is gender. Further, you may create a table for gender, so that's table and then tagay, $, and then gender, and you will see that 920 among 1,000 samples here who died because of alcohol were men. And further, you may apply the prop.test function by putting x equals 920 as seen on the table and n equals 1,000 since there are 1,000 samples. Or that is basically 920 out of 1,000, which is our p hat, which is x over n as 920 over 1,000. And under the null hypothesis, our hypothesized proportion, or P in R, is 0.75. And we are placing the option correct equals false, indicating that there's no correction needed since we're able to meet the criteria or the condition that n times pi here is at least 5. And that leads to this result in which the p-value is also less than 0.001. However, keep in mind here that this p-value is a two-tailed p-value. And the p-value here, based on this alternative hypothesis, we computed this p-value on the condition that this is a one-tailed test. Keep in mind that R always displays a two-tailed p-value in the z-test for single proportion. Thus, if you are performing a one-tailed test, always divide the p-value generated by R by 2. Now, regarding the test statistic, notice that although we computed z as 12.415 and R displays chi-square, which is 154.13, whatever is that, all we have to remember is that chi-square, when its df is equal to 1, is always equal to z squared. In other words, when you get the square of this value, rest assured that that is equal to that chi-square, which is 154.13, since its df is 1. Now, in the z-test for single proportion, you don't have to worry because the df here will always be equal to 1. So if you need the value of z, all you have to do is to get the square root of this value, and rest assured that is always the same as the value of the z-test in single proportion. Now, as for the confidence interval, the one that we computed is 0.903 to 0.937. Although that's just very close, the one that we computed is 0.903 to 0.937. Although we did not exactly reach the value generated by R, at least when rounded off to the nearest whole number when expressed in percent, it's also equal to 90 to 94%, which indicates that at 95% confidence interval, 90 to 94% of alcohol-related deaths were among men. And again, since this does not contain the value under the null hypothesis, that's why we rejected the null hypothesis. As for example number 2, wherein we are trying to determine whether the data provides sufficient evidence that the occurrence of Alzheimer's disease differ with men and women, and as you recall, 23 out of 90 women and 9 out of 80 men based on the samples have Alzheimer's disease. And our null hypothesis was that the proportions of Alzheimer's disease among men and women are equal, and that the alternative hypothesis is that the proportions of Alzheimer's disease among men and women are not equal, or in other words, the proportions of Alzheimer's disease differ among men and women. Now, for R, you may open the file alzheimer.rdata, and you may see its structure by typing str, then Alzheimer, or you may take a quick look of the file by typing Alzheimer. And you'll notice that there are two essential columns here, gender and Alzheimer, which you may create a table by typing table and then Alzheimer, $, and then one of the columns that say Alzheimer with capital A, and then comma, and then the file name Alzheimer, $, and then the other column which is gender. And you're going to see this result, which indicates that 23 out of 90 and 9 out of 80 have Alzheimer's disease. So using the prop.test function, all you have to type are 23 over 90 and 9 out of 80 under the X and N options in prop.test. And again, correct.false indicates here that we don't need a correction since n sub 1 pi, n sub 2 pi, n sub 1 1 minus pi, and n sub 2 1 minus pi, if you recall, are all greater than 5. And as you press enter key, you will have this result, which indicates that the p-value is 0.017, in which, as you can see, the p-value is exactly the same. It is because we performed a two-tailed test here. Remember that R always assume a two-tailed test, likewise in the z-test of two proportions. And as for the value of z, R generated a chi-square value, which is again is the square of the test statistic z whenever df is equal to 1. So in other words, when you try to square this value, rest assured that this value is the same as this value. So if you need the value of z, all you have to do is to get the square root of this chi-square. And again, do not worry because z-test for two proportions will always have a df of 1. Then as for the 95% confidence interval, since p hat 1 is 23 over 90 and p hat 2 is 9 over 80, then all we have to do is to apply this formula wherein we subtract p hat 1 and p hat 2, so that's 23 over 90 minus p hat 2, so that's 9 over 80 plus and minus 1.96 times the square root of p hat 1, which is 23 over 90, n sub 1, which is 90, then p hat 2 as 9 over 80, and n sub 2 as 80. And computing for that value, we're going to have 0.0294 and 0.2567, which is what R has generated as well. And what you notice is that this value does not contain 0. Thus, our null hypothesis implying equality between the two population proportions are equal was rejected. As for the last example, you may open the file neutropenia.rdata. You may take a look at its structure, and you may also take a quick look at the file by typing neutropenia. And what you notice is that there are two essential columns, which is the dengue severity, which is represented by the columns here, and neutrophils, whether it's normal, in other words, it's absent, and low, indicating that there's a presence of neutropenia. You may create a table using the table function, and then the two essential columns, which are neutrophils and dengue severity, and you will generate this table, which is exactly the same as the table that we had. And further, you may use the prop.test function by putting 0, 11, 7, and 8 as the value of x, and 10, 24, 28, and 28 as the value of n. And again, we're implying that there's no correction to be applied since we're able to meet that at least 20% of the cells here have expected count less than 5. And we're going to have this result, which is exactly the same as the one that we computed, as we can see that the p-value generated by R and the one that we computed are exactly the same, which is 0.054. Now, for the chi-square test statistic, notice that we also have exactly the same test statistic, 7.624. Even the DF is the same as 3. R also displays the 4 sample proportions, which are 0 over 10, which is 0, 11 over 24, which is 0.45, 7 over 28, which is 0.25, and 8 over 28, which is 0.2857. So again, this p-value indicates that we're not going to reject the null hypothesis and conclude that there's no sufficient evidence that the proportion of patients with neutropenia differ according to the severity of dengue fever. Now, do not be alarmed with this warning generated by R. It is because this warning is just an indication that at least one expected count is found to be less than 5. Now, without manually computing for the expected count, how do you know if how many expected counts have less than 5? Now, given this code that we submitted in R, all you have to do is to put a name on it. In this case, I am naming this result as result. So notice that this code here is exactly the same as this one. In other words, I just added this arrow and then a name before it. And then we may type result $observed, and what you'll notice that this table is exactly the same as this table. Now, for you to see the expected counts, you may type the same object name, in this case result $, and then expected. And R will compute for the expected counts so that you will see how many expected counts are less than 5. And since R here was able to see that there's an expected count which is less than 5, that's why this warning message was generated. And again, since as we can see here, we only have 1 out of 8, indicating that only 12.5% of the cells have expected count less than 5, then still, we may perform chi-square test of homogeneity. Now, if in case this assumption was violated, that would be the time that we have to write true. And that will be discussed on the next lesson.
If you learned in this video, you may click like, you may also subscribe. Thank you for watching and stay safe, guys.